Welcome to the 2021 BA Winchester webinar. Sadly, we're unable to hold an in-person event this year due to the pandemic, though hopefully we'll retain some of the Winchester feel with an excellent lineup of speakers and are starting off with a favourite of recent years. All the lectures are being held on Zoom and live streamed to YouTube, and the recordings will be available to watch on YouTube a few hours after the event. You can ask questions by typing them into the Q&A on Zoom or the comments in YouTube, and we'll answer them at the end of the presentations. It's my pleasure to hand over to Alan Dowdell, co-organiser with Anne Davies of the Winchester Weekends.
Thank you much, Andy. So I wish to welcome you to Winchester Weekend as a webinar. For all those people who normally attend Winchester Weekend over the last 55 years or so, you know the form, but for those who have never attended, or unfortunately never attended Winchester Weekend, the event is the residential meeting of the British Astronomical Association. It's held over just before or just after Easter in the Winchester. We hold it currently at a village called Sparshot just outside of Winchester, and it's from Friday through to Saturday and on to Sunday. And it's a weekend of lectures, meals, getting together, and even a bit of observing as well. So it's a great weekend, and hope in the future some of us who are seeing this for the first time can attend. I'd like to thank Anne Davies for organising this unusual Winchester Weekend. Organising the speakers and getting the whole thing together. She does all she organises the speakers and organises me for doing the Winchester Weekend, and I like to thank her for that. So this is a taste of the Winchester Weekend, and so what I want to do is to go through. We're going to have, first of all, a talk which is very popular for the weekend. We've introduced in the last couple of years as a sample. Then we're having a taste of a section meeting, and then later on this evening we will have the Alfred Curtis Memorial Lecture as our formal talk. Alfred Curtis was the person who organised and first ran this weekend some 55 years ago. So I would like to introduce our first presentation this afternoon. That is from a double act, and this works brilliantly well over the last couple of years. We'd like to thank Dr. Paul Abel and Peter Lawrence, who are going to do this double act for us. And it's going to be the challenges of observational challenges of 2021. We've had those, and you can see them on your webpage. We've seen these challenges before. Paul is currently the director of the Mercury and Venus section of the BAA, and he is a keen visual observer. I emphasize visual observer, and he actually still does drawings at the telescope, which is absolutely brilliant. Thoroughly enjoy that. And Peter Lawrence, of course, is from you've seen him on the Sky at Night programs along with Paul, and he's a visual, not a visual man, it may do, but he does imaging to high quality. So, and he does the practical side of the Sky at Night program. So without any further delay, I'd like to ask for that presentation. And I'd also like to thank again Anne for organising this, and also thank you. Don't forget your keys. So hand you over.
Thank you very much, Alan. I'm going to share the presentation screen as best I can. Let's go for it there. Okay. Well, welcome everybody. And for those who are familiar with this, this is our observing challenges for the upcoming year. We normally pick a number of challenges which vary in difficulty from very easy through mid-range to downright difficult. And we've done the same this year. We've got 10 challenges for you, so I shall stop waffling on and we'll crack on with them. Before we, I always put this slide in
every year
just to annoy him. Before we carry on, just to point out, because this is the British Astronomical Association and it's a good clearinghouse for observations, if you do make any of these challenge observations, then record the details about the equipment, etc., that you used, because that may be useful for other people in the future. Okay, so on with the first challenge, which is Venus at Dichotomy, and over to my colleague, Dr. Paul Abel.
Thanks, Pete. So observation number 1, Venus at Dichotomy. This might not sound like much of a challenge. After all, Venus is one of the brightest objects in the evening or morning sky. But there is a bit of a challenge associated with this one, as I'll now explain. So Venus is an inferior planet. That doesn't mean we think any less of it. It simply means it's closer to the sun than we are. And at the moment, I've got here a little plot which shows Venus in its orbit. On the 26th of March, 2021, Venus passed through superior conjunction. And that's position 1 on that little figure. And what will happen now is Venus has returned from, it was in the morning sky, it's now returned to the evening sky, and the planet will slowly move towards us. And as it does so, it will get bigger in size and the phase of the planet will start to decrease. And that will continue to happen until on the 28th of October, Venus should appear at 50% illumination. And this is what we mean by dichotomy. It means that the planet appears perfectly like a half moon if you were to look at it through a telescope. Now, why do I say apparent dichotomy or theoretical dichotomy? Well, that's because of a phenomenon called the Schroter effect. And it's well observed. In fact, the British Astronomical Association was one of the first institutions to recognize this kind of a phenomenon from its observational records. There is always a difference between the theoretical date when a dichotomy occurs and when it actually occurs. And this is due to the Schroter effect. The light, Venus, as you know, probably has a very, very thick atmosphere, and light is dispersed into it. And as a result, the theoretical phase is always slightly greater than the observed phase. Now, in eastern elongations, when Venus appears in the evening sky, this means observed dichotomy will occur later than predicted. And so to see Venus properly at dichotomy, i.e. where the terminator is a straight line, you will probably need a telescope for that. Although you can see the phases with binoculars, I think it's fair to say that 59% to 51% are going to look very similar in binoculars. So you will need a telescope to see it. And there's an extra challenge in that, unfortunately, Venus is going to be fairly low down in the evening sky when even by this time of year. So the best time to catch this is in the daytime sky. Now, catching Venus in the daytime sky does require a bit of skill. I will give my usual warning. If you're not confident or comfortable about observing Venus in the daytime, then please don't do it. The sun is a very dangerous object, and even a glimpse through a finder scope or pair of binoculars is enough to do a lifetime's worth of damage. However, if you are fairly comfortable with doing it, it's not too difficult to find a planet if you've got setting circles. You can see in the image there some right ascension and declination circles. I think that's on Pete's telescope. And you can use those to find the planet. It's fairly straightforward. First thing you need to do is put the cap on the telescope and on the viewfinder, on the finder scope, and then you can look up the coordinates of right ascension and declination of both the sun and Venus. Then all you have to do is slew the telescope towards the sun. When it's you take the caps off the finder scope and project the sun through the finder, and then cap it again. And then you simply rotate the telescope round the right ascension and declination of Venus. You'll need to set the dials beforehand when you found the sun, so you've got the right ascension and declination of the sun, and then you can just slew to the coordinates of Venus. And if you use a low power eyepiece, you will find that Venus is fairly easy to pick up against the daytime sky. Even with a low power, it becomes quite obvious. So when is the best time to look then? Well, we have there we go for the next slide. The best time to look is actually on Dichotomy, the date of Dichotomy, 28th of October. You'll see then, if you look on the WinDuPlus software that Pete's going to mention later, you'll see Venus is technically supposed to be at 50%. But if you look through a small telescope or even a large telescope, you'll see that Venus won't be. It'll be a little bit less than that. And if you continue to observe the planet over the next few days, you should be able to determine for yourself when Venus is precisely 50% illuminated, when the terminator appears as a perfectly straight line. You should do this in integrated light, in white light, because if you put on filters, you'll get slightly different dates. In particular, Dichotomy occurs really late if you use a violet or a blue filter. So it's best to do this either using a yellow filter or no filter at all. And then finally, I should say, send your observations into the Mercury and Venus section director, me in other words, because it's very, very useful to be able to determine the date of Dichotomy when it actually occurs.
And I should say we'll put Paul's email address up at the end of this presentation as well. Okay, so on to challenge number 2, and I've called this one the Saturn Moon Challenge. Now, this is to do, obviously, with Saturn and the fact that when you look at the planet through a telescope, even a small telescope, you'll see that it has a nice family of moons that you can look at. And this challenge is basically trying to see as many of the amateur-friendly moons as possible. Now, Saturn is quite low in our sky at the moment, which means that to get a detail on the planet from the UK requires that rare commodity, which is good seeing, and that doesn't happen very often. So chasing the moons is another option with the planet, just to see how far down you can actually go. Now, I've broken them into 3 different categories, which I've called the inner, mid, and outer moons. And those are my own titles for those moons to describe where these are in terms of amateur observations. Now, for the inner moons, the 5 ones which are regularly seen are shown here, and they sort of get more difficult as you get closer to the planet. So the 3 which are relatively easy are Rhea, Dione, and Tethys, which are about magnitude 10, so a small telescope will pick those up without too much bother, really. Then you go into Enceladus, which is a bit closer to Saturn and approaching magnitude 12. So that's a bit of a tougher target to aim for, but still quite doable. Mimas is really quite tricky to see visually because it's faint, it's about magnitude 13, and it's really close to the ring system. So the brightness of the planet tends to overpower Mimas and it'll be lost completely. If you have an imaging system, if you try and take an image of the planet, then the 4 outer ones of the inner moons, if that makes sense, are fairly easy, but that Mimas is quite a tricky one to pick out. As we head out, we go to what I call the mid-moons, and here we encounter the brightest of the Saturnian moons, which is Titan. And Titan is really easy. It's between Magna 8 and 9, so even binoculars will pick up Titan fairly well. And then you go out to Hyperion, which is much trickier. That's about the same magnitude as Pluto, about Mag 14, so you need a fairly big telescope to pick that one out. Then Iapetus is an interesting moon. It's got a much larger orbit, so you have to often look out further than the other moons, obviously, but it varies in brightness. It's called the yin-yang moon because it has 2 hemispheres of different brightnesses. One is dark, one is bright. And because it's gravitationally locked to Saturn, as it moves around the planet, we see those hemispheres presented in different ways. So when Iapetus is at the western elongation, that's when it's brightest, about magnitude 10-ish or so. But then when it goes to the eastern elongation, eastern side of Saturn, that's when we see the dark hemisphere and it dims to about magnitude 12. So that's quite tricky. So it can be a difficult one. So it's best to look up its position to work out where it's going to be, remembering that west is best. The outer moon, Paul laughed at this when I showed it to him when we went through this quickly yesterday, is Phoebe. And
it's magnitude 16, that's why.
Magnitude 16.5 is easy for anybody that's got decent eyesight. No, it's a tricky one visually. You need a really big telescope to pick this up. So this is better suited towards imaging. But Phoebe has a massive orbit, as you can see, compared to the other moons. and it's highly inclined. So you actually have to hunt it down. But as we go through June, it's quite close to where the other moons will be. So that's a good opportunity to try and get Phoebe with a camera. How do you find the moons? Well, WinJupos, there's the URL for downloading WinJupos. It's free, and that'll give you information about all the moons except for Phoebe, because it's impossible, of course. No, it's not impossible, but Phoebe is very faint. WinJupos will also give you the current magnitudes, because they do vary a little bit. This is a really good resource for finding out where the moons are and how bright they're going to be. Cartes de Ciel you can download for free as well, and that will show you the position of Phoebe. And there are even some smartphone apps such as Sky Safari Pro. I don't know about the lower ones, because there are different variations in Sky Safari whether they will show the position out to Phoebe. But it's a pretty good app for serious astronomy, so that'll give you the position as well. Saturn is improving in position. In 2020, it was very low down. In 2021, it's a little bit higher. In fact, it's out of that cloud, which is it's there for some reason. So that'll make the view a bit better for us.
Okay, thanks, Pete. All right, challenge number 3, an early partial solar eclipse. So the challenge, of course, might be in getting a clear sky for this. That tends to be the biggest challenge with any kind of astronomical phenomena in this country. But assuming we do, then there will be an annular solar eclipse, which occurs on the 10th of June this year. Now, an annular solar eclipse, a bit different to the usual total eclipse, when we have the beautiful totality and we can see the corona. When that happens, the moon and the sun are about the same size in the sky. But when we have an annular eclipse, the moon is slightly smaller in apparent size to the sun. And so we get this ring of fire, this annulus shape, and that's why it's called an annular eclipse. We won't be seeing totality from the UK. I've got here a chart, I think, by Fred Espenac. You can see the path of totality for this particular eclipse there. It crosses Canada and then extends to the far north. So we certainly will only get a partial eclipse in the UK. And the further north you go in the UK, the more you'll find, the more the sun is obscured by the moon. You'll also find the start and end times for the eclipse will vary a little bit depending on your location. But if you go to the BAA handbook, you'll find start times and end times and mid-eclipse times, all the essential details in there. But there is a difference, so it is worth looking up and checking from your location. For example, from London, first contact occurs at 09 hours 08 minutes 40 seconds UT, and we'll have about a maximum obscuration of 20%. But further north in Aberdeen, first contact occurs at 09:10 42 seconds, and there'll be 32.8% of the sun covered. So you should check out whereabouts you are. Now, something about this particular eclipse, which is a bit different this time, which makes it a challenge, and that is observing the moon against the spicule layer of the sun. You'll remember in a previous one of these I did, Pete and myself did for Winchester, we looked at Venus against the spicule layer. This time we're looking at the moon. And what is the spicule layer? Well, it's the upper atmosphere of the sun. So if you were to look at the sun in white light through a filter or project a telescopic image of the sun, that's the sun's usual photosphere that we see. But there's a layer of hot hydrogen above that called the chromosphere, literally the sphere of color in Greek. And the chromosphere is where this hot plasma, hot hydrogen is, and this is the spicule layer. And you can see it here on this image there. It's just this air, just above the edge of the limb of the sun. And what we're hoping to do in this particular challenge is catch when the moon just appears just above that particular region. So, well, how do we go about doing that? Well, for a start, to see the spicule layer, you'll need a hydrogen alpha telescope or a suitable hydrogen alpha filter, because as I've just said, the spicule layer only occurs, you can only see it in the hydrogen wave bands. So you'll need something like this kind of telescope, the Coronado, or the whatever HL filters you can get, which fit to the telescope. The other thing that's really important is to make sure that you know the orientation of the sun when you start to do this. The last thing you want to do is be sitting there and looking in the wrong direction of the solar limb, only for the moon to pass through in the opposite direction you're looking at. So it's best figuring out what the orientation is of the telescope a few days before you start looking. You'll need to know which way is north and the directions of east and west. And to help you do that, there's this link here, atoptics.co.uk. / tilt the sun, that will give you the orientation. I think it's a little app you can download, will give you the orientation of the sun. Now, in a mirror inverting telescope with no star diagonal, the moon will appear to pass over the sun's disk at the 7 o'clock position. And we'll get 2 attempts of looking for the moon against the spicule layer. The other thing to work out as well is to work out what the start time of it is, because you'll want to go out and start observing 10-15 minutes before first contact actually occurs. I've got some timings here for Leicester on the 10th of June. So on the left, you can see first contact is occurring at 10:07 BST, and you can see the moon is just eating into the solar limb there. And maximum eclipse occurs at 11:14 BST, and then we have last contact at 12:26 BST. So you need to work out your start times and the end times, and then start looking at the beginning of the eclipse, start looking 10-15 minutes before that. And what you look out for is to look for that area just above the sun's atmosphere where the moon is starting to eat into it. And then follow the eclipse through, because if it's cloudy at the start of the eclipse, or you didn't get it in time, you can always try again at the end of the eclipse. And that'll be slightly easier because you'll be able to watch the moon's disk pass off the edge of the sun, and you'll be able to catch it against the spicule layer there. So you get 2 attempts to do this. And I should say also, make a drawing or grab an image of this, because it's very, very rare to get an image of a partial eclipse of the sun in the UK, and certainly capturing the moon against the spicule layer from an eclipse in the UK will be very, very rare indeed.
Thank you, Paul. Okay, well, challenge number 4 is an old friend. It's a deep sky object, which is M57, the Ring Nebula, and I'm going to give you a new twist on its central star. Now, M57 exists in the constellation of Lyra, the Lyre, and this is a photograph of Lyra. It contains the bright star Vega at the top. Then you've got a nice equilateral triangle here, and this star here is Epsilon Lyrae, the double-double. You can see it visually split into 2 stars, but if you put a telescope on it, you'll see each of those split into 2 as well. This star here, that's Delta Lyrae, that's got a lovely star cluster around it. But our object sits between the bottom 2 stars of this squash diamond shape. If I go to the chart, you can see where M57 would be located. It's normally stated that it's midway between Sulfat and Cheliac, that's Gamma and Beta Lyrae. Actually, that's not quite true. It's slightly offset towards Cheliac and slightly below the line that joins those 2, slightly south of that line. So bear that in mind. It's quite an easy object to miss if you're looking for it at a low power, because it looks just like a star. And the trick is to find it, to identify what you think is M57, and then increase the magnification. And then if you've got it right, it should look like a disk. It's a class of object known as a planetary nebula, and that's because it looks a bit like a ghostly planet in the sky. If you've got a bigger telescope and a high magnification, you might be able to see it as a ring. It's got a hole in the middle. That's why it's called the Ring Nebula as well. This is a very rare thing. This is a sketch that I made of M57 many years ago, and that's what it looks like at low power. So it looks just like a star, but as you go up the power, that's when you start to see the ring effect there. Now, if you take a photograph of M57 these days, it's quite difficult not to capture the star which created the nebula. This is a low mass star getting to the end of its life, and it puffs off its outer layers into space, which creates this region which glows to us and appears as a ring or an oblate, typically an oblate glowing region around the central star. And it's the central star that I'm interested in. Now, the central star with a camera is a pretty easy thing to pick up. It's not too difficult at all, but it is visually quite faint. It's about magnitude 15 or so. So you need a big telescope to see it visually. But my twist is to take a photograph of the central star in M57 with a smartphone. That's a new thing for me. And to do this, you're going to need to couple your smartphone to your telescope. And the usual way of doing that is afocally. So that means you aim your telescope at the object you want to take a photograph of, and then you put the smartphone very close to the eyepiece and then press the shutter button. That works really well with the moon and with the planets, but it's not going to work so well with a deep sky object because it's very, very faint. So there's not enough light to trigger the automatic functions in your camera. So you're going to have to solve a few problems here. You're going to have to keep the camera nice and rigid. And the way to do that is to use one of these strange looking mounts, which are very inexpensive to buy off the internet, or if you've got a 3D printer, you can print your own mount. And basically they hold the camera in position. Once you've done that, you need to have an app on your camera which will allow you to get access to the manual controls of the cameras. Then that will allow you to set the ISO, or the gain, higher than normal. You need to be able to set a multi-second exposure, and you need to set the focus at infinity. And once you've done all that, you need to then press the shutter button without rocking the telescope. So there are two ways of doing that. You can either set a delay shutter release on your camera. So you press the shutter button, then you wait a few seconds before the shutter actually activates. Or you can use headphones which have got a volume control on them, because often the volume control will act as a remote shutter release. So that's another way of doing it. So if you can do that, hopefully, with a bit of experimentation, you can take a picture of M57 with your smartphone and also grab that lovely central star. This is actually a photograph taken by Hubble, not using a smartphone. And this is what the field looks like with all these star magnitudes marked. Here they're done in the classic way without the decimal point. So it's not magnitude 154, it's magnitude 15.4 for the upper one there. But the actual central star is about mag 15.3. I can hear something else talking there. The other star in there is even fainter. So if you manage to grab that in the central hole, which is offset from the center, that's magnitude 16.3, which would be pretty amazing for a smartphone. But give it a go, see what you can get.
Thanks, Pete. I'm just going to say something on the back of that, Pete. Did you say that you got the central star with a 4-inch telescope?
Yes, I did. The black and white photograph I showed there was with a 4-inch telescope. It's not a difficult thing at all.
No, that's always quite surprised me, because I've never seen it in anything smaller than a 15-inch telescope.
No, that's right. It's just a camera. A camera can do the integration and picks it out quite well.
Okay. All right. Challenge number 5, the moons of Uranus. As I'm sure everyone here knows, Uranus is the 7th planet from the sun, and it orbits way beyond Saturn in the outer frozen gloom of the solar system. It is, unfortunately, the best placed planet in the evening skies from the UK at the moment. Shouldn't complain, though, because we've just had an excellent Mars opposition. But Uranus is very, very well placed. It comes to a reasonable altitude, and you can find it amongst the stars of Aries. It comes to opposition on the 4th of November, and that won't be when it's at its brightest. It will be about magnitude 5.7 and have an apparent diameter of about 3.8 arc seconds. Now, although it has magnitude 5.7, and that is technically below the naked eye threshold to be able to see it without optical aid, I've never managed to do that. And I think for most people, you will need binoculars to be able to see it at all. But even in binoculars or a small telescope, the planet is actually quite easy to find. But for this challenge, we're not looking at the disk of Uranus or just being able to identify it. We want to be able to look at the moons. And for that, you will need, I think, at least access to an 8-inch telescope to be able to see them. I've seen 2 of the brightest satellites with my 8-inch telescope here, and larger telescopes will show you more of the satellites. So when is the best time to find it, and how do we get to Uranus? Well, there are a number of ways you can find Uranus. If you've got a go-to mount, then that's easy to do. All you have to do is set it up, and you can slew to Uranus directly. If you don't do that, there's another way of doing it, and that is to simply star hop from a prominent constellation. And as you can see in this little chart here, we have the Pleiades and in Taurus up there, and Aries is just here off to the right. And what we have to do is just get star hop into Aries. So if we take a closer look at that constellation, we can locate the star Sigma Ariatis, which is a bluish-white star. Then we star hop simply to Omicron Ariatis, and you should see Uranus nearby in your finder. It will be quite obvious. If you use a low power eyepiece on your telescope, it will be very, very obvious. It will be this greenish bluish disk amongst the stars of Uranus. And once you've located it, it's not too difficult to follow it night after night because it moves very, very slowly in the outer solar system. Well, when is the best chance to look at the moons? Well, it is, of course, when Uranus is at opposition. And when this happens, Uranus and the Sun are in opposite parts of the sky, and Uranus will be at its brightest in this particular opposition. And as I've said, that will occur on the 4th of November. So it's not just Uranus, but the moons will be at their brightest as well. And I've got here a little graphic from WinDupas, which shows the orientation of the moons at about 11 o'clock in the evening on the 4th of November. And they are quite faint. Visually, to see them, as I've said, I've only seen Titania and Oberon with my 8-inch telescope. I haven't yet looked at it with my new 12-inch telescope, but I'd expect to be able to see down to Umbriel. And this is the 5 main satellites we've got in order of magnitude there. So Titania is the brightest at magnitude 13.9, then Oberon at 14.1, Ariel 14.3, Umbriel 14.9, and then finally Miranda at 16.4.
Phoebe level.
Yeah, Phoebe level, so I shouldn't have included it. But it is quite a challenge to see. I think you would pick them up, all of them, in a 16-inch telescope. But with an imaging setup, I guess you could image all of those satellites with quite a modest telescope. Is that right, Pete?
They're not too difficult, actually. The biggest challenge is getting a big enough image scale that you can actually have them all separated from the planet. And then the problem becomes the brightness of Uranus, which, if you've got any haze in the sky or mistiness in the optics, it will spread the light out and it will hide, especially Miranda. Miranda's quite tricky. Right, so there we are. There's 2 attempts. You can either try and visually see how many you can see and then take an image. And it would be interesting to know how many of these satellites you can see on the night of opposition or nearest opposition. I mean, it's not going to make too much difference to the magnitude if you look a couple of days either way. So it'd be interesting to see how many of these satellites people can see. Okay, well, this is a very moon-heavy presentation this year, and the next one concerns our own moon, and this is about thin moon hunting. So this, I'll just refresh your memory on the lunar phases. The lunar phases occur because of the ever-changing angle between the moon, the Earth, and the sun. When the moon lines up with the sun in the sky, it'll either give us an eclipse, very rarely, or it'll normally head above or below the sun. But that's a position known as new moon. And then as the moon approaches that position, it appears a really thin crescent in our morning sky. And then after that position, it appears as a really thin crescent in our evening sky. And the challenge is to try and see these. There are some good opportunities in 2021. So this is actually the phase diagram. You can see when the moon is on the opposite side of the sky to the sun, the moon will appear full. It's at opposition at that time. And when it's lined up with the sun, we see the dark side of the moon pointing towards us, so we can't see the moon at all. And the thin moons, which I'm interested in, are the waxing crescents just after new moon and the waning crescents just before new moon. Now, there is a limit to the theoretical limit, which dictates when you should be able to see the moon's crescent after new moon and before new moon. And this is called the Danjon limit. So basically, the separation from the sun has to be in excess of 7 degrees to actually be able to see the crescent. Now, having said that, I know in the past that there have been specialist attempts at imaging the moon at the new phase. I'm not talking about an eclipse, but actually when it's properly at new, either above or below the sun. I think Thierry Legault managed to get an image of the moon at that point using specialist equipment with infrared filters, I believe. So maybe it's worth testing the Danjon limit. This is a picture of the waxing crescent moon with earth shine, beautiful colored sky there. But that's actually quite an easy waxing crescent, as is this one here, hiding amongst the clouds. The one I'm talking about is going to be much thinner, something like that, where you've just got this thin arc of light. That was the evening one. This is the morning one. So it depends whether you fancy getting up early in the morning to grab it. They can be really difficult. This is a waning crescent in the early morning sky above that's the Selsey lifeboat station there, which has now been demolished, sadly. But that moon there shows off nicely that this thin arc of light is really difficult to see because the sky is really bright behind it. This is an attempt I did where I managed to capture it at 19 hours, 14 minutes after new moon. That's what's referred to as the moon's age. It's not its real geological age, but actually the time since the last new moon. So that's not a bad attempt. But interestingly, this one here is actually slightly later. So the moon should be easier to see, but it wasn't. It was harder because the sky was hazier. So you have to get really good conditions to actually be able to pick out this thin crescent. I think, Paul, you were struggling to see that arc of...
All I could see was noise, Pete, but you assure me it's there, so I'll believe you.
So rude. This is my record so far, and I've never seen one earlier than this, I have to say. So there's a challenge for you to beat this one, which is, this is 15 hours, 13 minutes after new. And that was very difficult. So you can see it in the image there. It's just really, really difficult to pick out. Look, Paul, look, adjust your screen. So here are some upcoming thin moon dates, and they're color coded for difficulty. So orange is difficult, green is easy, and red is theoretically impossible. So the August ones are below the Danjon limit. So if you want to test that limit, that's the time to do it. So have a go at that.
Thanks, Pete. Okay, challenge number 7, the Rilles of Gassendi. And I think this is probably a very easy challenge because I was conscious that some of the things we put in this year are going to require a bit of attempt to go out and see. But the Rilles of Gassendi actually is fairly straightforward. Even if you've got a very, very small telescope, you should be able to pick them out. So where is Gassendi crater? Well, it's a large impact crater located on the northern edge of the Mare Humorum on the moon. And it is quite a large impact crater. It's about 110 kilometers in diameter, but like a lot of lunar craters, it's actually quite shallow compared to its diameter. So it's only about 1.9 kilometers in depth. And I think it was one of the considered landing sites for, I think, Apollo 17. I wouldn't swear to that, but I think that's true. But in the end, they chose somewhere else. It's quite a distinctive crater. It's flooded with lava from the Mare. And you can see on the northern wall there, it's got another impact feature, which is Gassendi A, which overlaps its northern wall. And it's best seen when the terminator isn't too far away from it, because that throws some shadow onto it. So that in the evening sky is when the moon is just a few days from full, when it's about 81% illuminated. And I've got it there in the little box on the screen. Now, it's quite a remarkable feature. In fact, it's one of my favorite lunar formations on the moon. It shows a wealth of detail, even in small telescopes. There's 2 images here, which nicely show the rilles. Rilles on the moon are caused by a number of phenomena. They can be the result of collapsed lava tubes that have happened. They can be places where the land has sunk due to a volcanic fault, or they might be a hybrid of the two. And you can see that they're best seen here in these shots when there's some shadow making them a lot more obvious. The image on the left here, this is by the Lunar Reconnaissance Orbiter. It nicely shows these the rilles all over the floor of Gassendi. And on the right-hand side is an Apollo shot. And again, you can see they come out quite nicely. So it's not so much telescope size that you need. It's more steady seeing to be able to see them. And they are a splendid sight telescopically. Here's a drawing I made on the right-hand side here, not too long ago, on the 24th of March with my 12-inch telescope, but I've certainly had a very good sight of the rilles on the crater floor here with my 8-inch telescope as well. And as I say, you will need a telescope to be able to see them, and they're best detected when they're filled with shadow. And if you've got particularly good seeing, you should be able to trace the rilles quite a long way. If the seeing isn't particularly good, then you'll have to use lower magnification, and it might only be the deepest or the largest parts of the rilles that become obvious. Now, typically, they're best observed when there's some shadow in the crater. As you can see, we've got shadow on the wall there of Gassendi, and Gassendi A itself is also filled with shadow, and that is about 80% illumination. You can work out when that time's going to occur by using the Dial Moon software. If you type into Google Dial Moon 2021, it'll come up with this NASA website. All you have to do is input the date and time, and it will give you a high resolution image of what the moon looks like at that particular date and time. And it's quite useful because you can then click on the image, and because it's high resolution, it blows up and it will label a lot of the prominent lunar features. And so your best thing to do is to try and get it when the crater looks something like this, when there's a little bit of shadow inside, because that's when the rilles will be best illuminated. This is an evening project, but you can also do it in the morning sky, but you'll have to get up quite early because you'll want the terminator close by, but on the other side, which is when the moon is sort of coming towards the end of its lunation. So you need to get up early in the morning to try and get it. And if you want stable seeing, then the best time to do this is probably towards autumn and winter, because during the summer months, the moon is fairly low down, both in the morning and the evening sky. So this is probably a good project to try towards the end of the year when the moon's a little bit higher in the sky. But if you get some good seeing, you should be able to pick out the rilles. This is, I think, Pete snooking one of his images there because he couldn't bear for there just to be drawings. Actually, quite a nice image. You've got some of the little impact craters in there as well. It really is a striking formation. So regardless of your telescope size or whether you draw or whether you image, go out and take a look and see for yourself the Rilles of Gassendi.
Thank you, Paul. Yes, so we're back to smartphones again for challenge number 8, which is to do with NLCs. So what are NLCs? Well, quickly, these are noctilucent clouds. These are the highest clouds on the Earth. They form in the northern hemisphere, typically from late May through to early August, at a height of about 82 kilometers, about 50 miles up. And at that height, these ice clouds, because they're made up of tiny ice particles, are able to reflect the sun's light when the sun is between 6 and 16 degrees below the horizon. So as the deepening twilight in the evening or brightening twilight in the morning occurs, you sometimes see these clouds shining away. And if you've got dark tropospheric clouds in front of them, they make a striking contrast, because the tropospheric clouds are so low down, they don't get the sun's light. They don't catch the sun's light. So noctilucent clouds are a summer phenomenon, which is good because, of course, in the summer, we don't get an awful lot of dark skies. Now, when you go out and you see NLCs, there were some fine ones last year. Not every night is guaranteed to have them. People do get excited if they are there. So there are lots of places online which will give you an indication that something's happening. If you go out, you look typically 90 to 120 minutes after sunset, low in the northwest, or a similar time before sunrise, low in the northeast. If they're there, then you'll see them shining away. And the typical way of photographing them is to use a DSLR and get a lovely photograph like this of them reflecting in some water. That's very nice, sets them off very nicely indeed. They're bright, so you can see them in urban conditions. Here we've got street lights and we've got NLCs in the background, so they stand out well against street lights. And this is another photograph taken with street lights. These bright blobs you've got either side here are the lights glowing from street lights, and the NLCs are very clear even in that sky there. Now, a couple of years ago, I was in Leicester with Paul, and we went out for a Chinese meal, and there was a bright NLC display that kicked off just as we were having the meal. And the biggest challenge then was I didn't have a camera with me, or a normal camera, only my phone, and B, we had to try and get out of the restaurant without looking as if we were trying to do a runner. And in the end, we managed to get outside, and we took most of the staff with us, and they were outside looking at the NLC display as well. But this was a photograph taken in the city of Leicester of the NLCs, and you can see they came out fairly well, even with a smartphone. So it made me wonder how well you could actually do. One of the problems with smartphones is getting the damn things to automatically focus correctly. And here's a photograph trying to focus on NLCs, and it's slightly out of focus. You've got the bright glow, but you've got not a lot of definition there. This is a photograph from last year. This is Comet F3 Neowise with a smartphone, and you've got the NLC hanging across the reservoir that's near to me at the moment. And this is a photograph again taken with a smartphone, which rivals the photograph I took with the DSLR, which was the first picture I showed. So I'm quite pleased about that. So basically, it's getting out there and seeing whether you can take a photograph. So what do you need to do? Well, you need to set your camera. You need to get one of those apps again, which I mentioned earlier, for taking the photograph of M57 Central Star, which gives you control over the camera. Set a highish ISO, set a multi-second exposure. You'll need a stable platform, so something like one of these cheap holders on a little mini tripod will do the trick, and then the remote shutter release again, where you use the volume control on headphone cables to release the shutter is an ideal way of doing it. So fingers crossed we get a display, and see if you can get it with a smartphone.
Thanks, Pete. Okay, the next challenge is an interesting challenge in that observationally really straightforward, but there is a little bit of mathematics involved in getting the answer. And this is calculating the distance of delta Cephei, which you can do in your back garden with a pair of binoculars, providing you're willing to use a scientific calculator to calculate 10 to the power of something. So how do we go about doing that? Well, let's just have a look at what delta Cephei is, because it's quite a remarkable star. So it's a bright variable star in the constellation of King Cepheus. It's there. I've got a little chart there that shows it's there in the box. It's in Cepheus, so it's a circumpolar star, so it's visible all year round. And it's a star that varies in magnitude. It varies from about plus 3.5 to plus 4.4 over about 5 days. So you can view it with the naked eye or with a pair of binoculars. Telescopically, it's very pretty because it's also a double star, and it's a very, very easy object to measure. Now, what makes it such an interesting object is the fact that delta Cephei is something called a Cepheid variable. It's a prototype of a type of variable star where there is a very well-established relationship between its intrinsic brightness, called the absolute magnitude, and its distance. And in particular, because there is this relationship between magnitude and distance, there's also a relationship between the absolute magnitude and its periodicity. So here we are, we have a nice plot here that shows the relationship between how the periodicity in days and absolute magnitude. And by period, I mean the time it takes from the star to go from its magnitude where you first observed it, it'll brighten up and then return back to the magnitude that you first started looking at it, which I say is about 5 days. And you can see we've got two plots on here. We have the blue plot and the green plot. We want the blue plot for this star because it's a traditional Cepheid variable. The green plot here is for older stars, population 2 stars, stars you find in globular clusters. And all you have to do once you've measured how long it takes the star to go for its period, say it's 10 days or 20 days, is you just simply go down 10 days and then up to the top of the blue curve and read off what the absolute magnitude is. All right, well, why does that help us? Well, it helps us because there is a very simple, I would say elegantly beautiful mathematical relationship between absolute magnitude, apparent magnitude, and the distance to the star, which is d. And it's given by this expression here. So m minus big M plus 5 equals 5 log d. Little m is the apparent magnitude. That's how bright the star appears in the evening sky or in the morning sky. Big M, the absolute magnitude, is how bright that star would be if you were standing at a distance of 10 parsecs from it. And since we want to work out what the distance is here, we have to rearrange this equation. I'm not expecting you to do it. I've done it for you. And all you have to do is divide through by 5 and take the inverse of log to base 10, which is just 10 to the power. And you'll find that this calculation here is easy to do on Google Calculator. There's a scientific calculator that will allow you to do 10 to the power. All we need to do then to calculate the distance to the star, in this case, delta Cephei, is put in its magnitude, its apparent magnitude, its absolute magnitude, and then work out that value of d. And then finally, we multiply by 3.26 to convert this distance in parsecs into light years. Okay, so how do we go about measuring the period from it? Well, that's a fairly straightforward thing to do, and it uses a standard tried and tested method that you can find all about in the British Astronomical Association variable star section website. Making visual estimates, magnitude estimates of stars is very easy, but if you've never done it before, if you go to the variable star section website, there's lots of introductory material there, how to do it. Basically, you take a chart like this. This is one I produced from the AAVSO, and you'll see there it's got the magnitudes on in the same format that Pete put on for Saturn's moons. And what you do is each night, over a course of about 5 or 6 days, you just measure the apparent magnitude against one of these stars and deduce its apparent magnitude over the course of each night. And if you do this for 5 or 6 nights, you'll get what is called a light curve. And here we have a light curve. You've got date on the bottom, the magnitude on the top, and you can say we get this sort of wavy sinusoidal period. And from this, we can tell how long it takes for the star to return back to its original magnitude. And for Delta Cephei, that is about 5 days. So you'll need to make observations of the apparent magnitude of Delta Cephei over about 5 days to confirm that it has this period. Once you've done that, you can then go back to the chart and work out what the absolute magnitude is. We've been doing a lot of teaching online in the university, and I've discovered my students really love worked examples. These are where I practically give away the answer on how to do it. So I've done the same thing here. So this isn't for Delta Cephei, this is just the general idea. So imagine that we've been making these magnitude estimates of a star, and we find that it takes 10 days on average for its magnitude to go back to its original values. So we would have here, we would go up to 10, as Pete's just doing there, up to the blue curve. And we see that means that this star then, this particular Cepheid, must have an absolute magnitude, big M, of about minus 4.1. We could also look up its apparent magnitude and find that that's 3.5. And those are the values we now put into our calculation. So the original one is 10 to the M minus big M plus 5 over 5. So if I put those numbers in, I find that D, if I put that into the calculator, gives me 331.13. And that's in parsecs. I want to convert that into light years. So I simply multiply by 3.26. And that converts this. And we find that our variable star is about 1,079 light years away. This particular star isn't the only example. You can do this for other stars in the night sky. There are other Cepheid variables this will work for. So RU Cam, R Scuti, RV Tauri, AL Virginis, and W Virginis. You can use exactly the same method. You just need to work out what the periodicity is, so how long it takes for it to vary in brightness. You can then use that graph to work out the absolute magnitude, substitute those values into the formula, and get the value of the distance. So you can use a pair of binoculars to calculate the distance to the stars just from your own back garden.
Fantastic. Well, we've reached the last challenge here, which is imaging a Galilean satellite eclipse. Now, Jupiter has a large number of satellites, but only 4 are easily visible with smallish amateur telescopes. And they're shown in this photograph here. You can see more dots than just 4, and that's because the camera has picked up fainter field stars. But the brighter 4 dots you can see there are known as the Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto. And they whiz backwards and forwards around the planet. And they're a wonderful thing to look at if you have a small telescope, seeing these little dots moving backwards and forwards around Jupiter. Now, these moons can interact with Jupiter, so they can cast shadows onto the planet's atmosphere. So you've got Io casting its shadow onto Jupiter's atmosphere here. They don't rock backwards and forwards like this normally. This is the GIF repeating, I should point out. And then up in the upper left corner, you've got Ganymede, which is actually disappearing into Jupiter's shadow. And you can see the curvature of Jupiter's shadow, and you can see the disk of Ganymede there. Now, Jupiter has an axial tilt of about 3.1 degrees, if I remember correctly, and that means that its seasons aren't as pronounced as our seasons are on Earth, but it does go through the usual sequence of 2 solstices and 2 equinoxes. It takes Jupiter, was it about 11.8 years, if I remember correctly, to go around the sun. And so over that period, roughly every 6 years, it'll have an equinox, and roughly every 6 years, it'll have a solstice as well. Now, when it's near a solstice, the orbits of the Galilean moons, which are virtually coplanar with Jupiter's equatorial plane, appear to us here on Earth as narrow ellipses, as you can see here. But when we're close to an equinox occurs when the sun appears on Jupiter's equatorial plane, as you were looking from Jupiter. We get the similar sort of view. So those orbital plane, all those orbital ellipses tilt down, so they look just like a line running across Jupiter. So the moons appear to move backwards and forwards along a line. And something interesting can happen then, because the moons can appear to interact with each other. They can appear to cross over each other, which is an occultation, or they can cast their shadows onto the disk of another moon, which is an eclipse. And these events are called mutual events, and they occur around a Jovian equinox. And the next Jovian equinox is at the beginning of May 2021. If you go online, you search for Jovian mutual events, you'll see various sites giving you lists of these events. This is a French site. You can go on here, you can generate an ephemerides of which shows the events which are happening for your location at any particular time. So there's lots of ways of finding out what's actually going on. There's the URL for it, and I think this will go up online anyway, so you can take your time and pull that down from there. If you've got a bigger telescope, you can image the Galilean moons and show them as disks. This is Ganymede from 2010, imaged. It's got a diameter of 1.8 arc seconds. You can see the disk quite clearly there. The one on the left is a simulation for comparison. And mutual events, when they occur, they can be fascinating to watch. This was actually an occultation of Io occulting part of Ganymede, and then Io cast its shadow on Ganymede, as you can see here. So there is a little dark patch running across Ganymede's disk, and what the challenge is all about is getting a better image of such an event when they occur. There are various such events due to happen fairly soon. On the 6th of May, Io's shadow eclipses Europa, so that should be quite a nice one to go for. And then on the 29th of May, Ganymede's shadow eclipses Io, so that's another one to aim for. But if you've got a small telescope and you're thinking, oh, come on, I'm not going to be able to see any of this. Well, yes, you can, because there's another event on the 14th of May where, again, it's Ganymede's shadow is partially eclipsing Io. And what you'll see through a small telescope is that Io will dim in brightness as this event is happening. So that's an observation as well. So if you haven't got a big telescope to take a picture of the shadow crossing the disk of a moon, then just observe the dip in brightness. And that, I think, brings us to the end of our challenges. We've got about 3 minutes left if anybody wants to ask any questions. And I think Andrew's going to come back in and ask those questions.
Great, thanks very much, Pete and Paul. That was an excellent set of challenges. I was particularly interested to see Paul's one on variable stars, as that's something which is close to my heart, if a little more technical.
Well, it's not actually that technical. I'm going to ask our first year students, amateur astronomers at Leicester University, to have a go at this. Be interesting to see. They're a pretty good bunch, and I'm sure they'll be able to manage it. And it's actually not difficult, as you know, to measure the brightness. And then all you're doing is looking up on the chart. If anybody is not sure about that formula but really wants to have a go, please just email me. I'm happy to explain in greater detail how it's done.
Thanks, Paul. It's kind of one of those things where you start to do the science as well, which is fascinating.
Yeah.
So we've got 3 questions and a comment come in so far. So first of all was from Steve Brown, right at the beginning, saying that he loved the cat. Yeah,
Pete puts it in every year. He likes the cat.
Well, I think we should show that again, shouldn't we?
No, I don't think we need to show it. Oh, for heaven's sake.
I should have added a poll to the event so we can see who wants to see the cat again. Excellent. Then we have a question from Darryl Dobbs. Is a 90mm refractor any use for observing Venus? He usually uses it for white light solar observing.
Yes, it absolutely is. You'll be able to see the phases. One of my earliest telescopes actually was a telescope slightly smaller than 90mm. You'll be able to see the phase of Venus, and if you're sensitive to the bluer end of the spectrum, you'll be able to see these dusky markings that appear in the atmosphere, as well as the bright cusp caps which wax and wane. Because we now know that the polar regions of Venus, the upper atmosphere, are incredibly dynamic places. So yeah, you should be able to see quite a few things. Have a go at making some observations and send them in to me. I would very much welcome that. And you can, I'm sure you can image a variety of phenomena on Venus as well with a 90mm telescope.
Yeah,
is that right, Pete?
Yeah, and of course it gets a lot better after you've gone past dichotomy, because the disk size, the apparent disk size, increases quite dramatically. It's part of my favorite section of observing Venus is when it's in its sort of crescent phase, and a 90mm scope is perfectly adequate for that.
Great, thank you. Oh, and I'll just add, if anyone wants to ask a question, you can do it in the Q&A at the bottom of Zoom. So we're then on to Stephen Beath. How do you define the absolute magnitude of a variable star?
With some good astrophysical model. I was afraid somebody might ask that. I was wondering if Pete might ask me that just to try and throw me off course. You have to, well, it's because it's varying. You have a range of absolute magnitudes, but it doesn't matter enough because of this periodicity to it. You still can get an intrinsic brightness of the thing. Obviously, it will be brighter when it's brighter, and smaller, fainter when it's fainter, due to the nature of this type of star. But you can then provide a lower and upper limit for an intrinsic brightness to these types of stars. It's also the case that that affects apparent magnitude as well, because this star varies from, I think, magnitude 3.5 to 4.4. You'll need to take an average of that to get the average magnitude to put in the formula. But you can see as well, if you go back to that periodicity, it doesn't matter too much that the absolute magnitude is varying. It's the periodicity that's related to the absolute magnitude. So by and large, it should be fine.
Great, thank you, Paul. And we don't actually have any more questions yet. We do have some thanks coming in on the challenges from Stephen Brown and Stephen Beath, just saying thanks for the explanation, Paul. And I'm pleased to say we have a good number of people who've been in attendance today. So between 140 and 150 across Zoom and YouTube.
That's pretty good. That's about as many as we normally get at Winchester, isn't it, Andy? Is it about those sorts of numbers?
I think typically we're limited by, I can't quite remember, it's kind of a mix of the hall and the accommodation. I think it's around 110 or so, maybe max out at 120 who can actually be there. So yeah. It's a good representative number.
Okay, good.
Great. Well,
we'll put this up online afterwards, won't we, Andy? And I can produce a little document to summarize each of these challenges if that's going to be helpful, and we could put that online as well.
Oh, excellent. Yeah, we can add that to the BA website.
What I would like to say, just before everyone disappears, is send me your observations, because what Peter and myself would like to do is include in next year's Winchester talk some of the people's attempts at some of these challenges. I think that would be quite nice to do.
Yes, so please do send your observations to Paul, and also add them to the BA website if you have if you've got a BA website account where you can add them to the members pages. We also have Dundee Astro saying thank you. What I'm going to do in a minute, I'm just going to, I'll leave the Zoom open because we may as well until 3:15, but I'm going to close up the YouTube and then restart it as the Exoplanet Division meeting. And what that'll also do, that'll also trigger Pete's and Paul's presentation to start processing on YouTube. So it should be available, I think, almost instantly. Then I'll do some editing later on to cut out our chit chat at the beginning before the start.
Okay.
Great. Thanks again.
Thank you very much.
Thanks for having us. Thanks.
And we'll reconvene at around 15:15 when we'll be having the Exoplanet Division meeting.
Cool. Thank you very much.